In this video, we will discuss calculations associated with electric fields and Coulomb's law. We will see how to calculate Coulomb force for a system of point charges. Let's look at the first problem. An electron enters midway into the region where you have this electric field. So the electric field is created by a couple of charged plates, a positive plate on top and negative plate at the bottom. Hence, the direction of the electric field will be from top to bottom. The electron enters this region midway, so this distance is 1 centimeter. Midway means half centimeters from the edge of the top plate or the edge of the bottom plate. Because the electron carries a negative charge, it will be attracted towards the positive plate, so it will gradually deflect. The path of the electron will gradually bend towards the upper plate like that. Now the condition is, if the electron misses the upper plate as it emerges from the electric field, what should the magnitude of the electric field be? Namely, if the electron just misses the top plate and gets out like that, what should this be? Let's look at the free body diagram for this electron. And of course you have this electric force acting on this electron given by the product of the electronic charge E times the magnitude of the electric field that we want to compute. So because that is the only force acting on this electron, there will be naturally an acceleration along that direction. And this acceleration can be computed using Newton's second law, ma equals electronic charge times electric field. So the acceleration will be E over m times the electric field magnitude. This is the charge of the electron. This is the mass of the electron. As you can see, the acceleration is a constant. So we should be able to use the principles of kinematics to solve for the magnitude of E. Now first note that the force acting on this electron is purely along the upward direction. So there is no acceleration along the horizontal direction. Let's take the horizontal direction to be the x-axis and the vertical direction to be the y-axis. So the x-coordinate will vary in a following manner. X equals to ut, where u is given by that. It is the initial x component of the electron's velocity. As the electron travels from this point until it gets out of the electric field, it would have traveled a horizontal distance of 2 centimeters. So convert that into meter, 0.02 meter equals u is 6 million meter per second. And the time it takes, let's assume it's capital T. So capital T is quite simply 0.02 over 6 times 10 to the power 6 seconds. Now the y part. In the same time, the electron would have traveled a vertical distance of half centimeters. So the expression for the y coordinate from kinematics is half a t squared. There is no initial y component to the velocity, so it stops there. Since we know in time capital T, it would have traveled a distance half centimeters with this much acceleration. Putting everything together, we get y 0.005 meter, half cm converted into meter, equals half. The acceleration is electronic charge, magnitude of the electric field that we are interested in, over the mass of the electron. And T is now the capital T squared. Now we know what capital T is. It's this number right there. The electronic charge is 1.602 times 10 to the power minus 19 Coulomb. The mass of the electron is about 9.11 times 10 to the power minus 31 kg. So let's substitute this information in here. We know what T is, and we can solve for the magnitude of the electric field. And when you solve that, you will get the following value for it. 5,118 newtons per coulomb. And that solves the problem. Problem 2. You have 3 charges, Q1, Q2, Q3, all with strength 6 nanocoulomb, and they are all positive charges. They are placed on the corners of a square whose sides is 0.2 meters. And then we bring in a 4th charge, a 4th negative charge, capital Q, and place it at the 4th corner. The magnitude of that charge is 2 nanocoulomb. What we are interested in is to find the net force on this charge due to the other 3 positive charges. So there are 3 contributions. The first contribution is, since Q1 is a positive charge and this is a negative charge, Q1 will tend to attract capital Q in that direction. Likewise, Q3, which is also a positive charge, will try to attract capital Q in that direction. And finally, Q2, again a positive charge, will attract capital Q along the diagonal direction, like that. Let's label the forces. The first force, let's call it F1. The second one is F2 and F3 respectively. For later use, we also have to realize that this angle here is 45 degrees because we're dealing with a square. And so this must also be 45 degrees. So let's calculate the vector F1, the first force. That's given by Coulomb's law. So the constant K, which is 9 times 10 to the power 9. The product of the 2 charges, now Q1 is 6 nanocoulomb, Q2 is 2 nanocoulomb. So when you multiply them, you get 12 times 10 to the power minus 18 after converting that into coulomb. The distance between them is L. L is 0.2 meters, so 0.2 squared. Notice the direction of F1 is leftward, so that's going to be minus I hat. Now let's do F3 first. F3 is vertically downward, this guy right there. And the expression is given again by K. The product of the 2 charges is again 12 times 10 to the power minus 18. That is the product of this strength and that strength of charges. The distance is again the length of the square, 0.2, and square that. The direction of F3 is vertically downward, so it's minus j hat. So I hat and j hat are unit vectors along the x-axis and y-axis respectively. Finally, F2. Now F2, the magnitude, let's calculate the magnitude first. It's K. The product of the 2 charges is the same as before, 12 times 10 to the power minus 18. The distance between this charge and that charge is the length of the diagonal of the square. And that, using Pythagoras' theorem, is quite simply 2L squared, square root. So the square of that is quite simply 2L squared. We know what L is, so L is 0.2, so 0.2 squared. Note that this F2 has a negative y component going like that, and negative x component going like that. So let's call this F2y, and this is F2x. Now F2y is quite simply F2 times the cosine of 45. So cosine of 45 is 1 over square root 2. It's going in a minus direction, so that's going to be minus j hat. Likewise, the x component is this magnitude times the cosine of that angle, which is also 45 degrees. So it is 1 over square root 2 in the direction of minus I hat. So the net force on capital Q will be the result of adding F1, F3, and F2. Note, I will go with I and J will go with J, and the result will be the following. So in taking the sum of F1, F2, and F3, we have separated the I hat from the J hat terms. Since this is just a two-dimensional vector, we can compute the magnitude of this force, and that will give you 5.17 times 10 to the power minus 6 newtons. Now what about the direction? Note the x component and the y component have the same value, but they are both negative. That means the x component is going like that, and the y component is going like that. And they have the same value, so this angle here, let's call it theta, must be arctangent of 1, which is 45 degrees. So the direction of this net force on capital Q is going like that. So the direction is towards the opposite corner. And that solves the problem. Problem 3. Now you have a couple of charges, Q1, which is a positive charge with magnitude 8 nanocoulomb, and Q2, which is a negative charge, is the same magnitude, 8 nanocoulomb, are placed along the x-axis 10 centimeters apart. We want to calculate the electric field these two charges produce at point P, a distance 12 cm from the first charge and 12 cm from the second charge. So the electric field that this positive charge creates at point P will be going in that direction, like that. And the electric field that Q2 produces at point P will be going in that direction. Now note, this angle right here is alpha, because it's the same as that angle, and this angle is also alpha, the same as that angle. So this is the midpoint, so that means this side is 5 cm, and that is 5 cm. So for later purpose, cosine alpha, which we shall just label as C alpha, is quite simply 5/12. Let's calculate this field first, due to that positive charge. So the electric field due to the positive charge, let's call it E1, is K, the constant, 9 times 10 to the power 9. The strength of Q1, which is 8 times 10 to the power minus 9, it's nanocoulomb. Now we are calculating electric field, so there's only one charge on top, not product of charges. And we divide that by the distance from the charge to the point of observation, 0.12 meter squared. Note it has positive x component and positive y component, which we can calculate. The x component is cosine alpha I hat, and the y component is sine alpha j hat. Alpha is given by this expression. Now the field due to Q2, so let's call that E2. It's given by K, the magnitude of the charge is again 8 times 10 to the power minus 9. The distance is still the same, 12 cm, convert that into meters squared. Now the x component, again, it's going to the right, and the y component now it's negative. So x component is cosine alpha I hat, y component is minus sine alpha j hat. The net field at point P is obtained by adding this and this. So you see that the y components will just get cancelled, leaving only the x component. So adding them, the x component doubles, and you will get the following for that value of the electric field. 4,167 I hat newtons per coulomb. So the net electric field is in the direction of I hat. Now let's assume for a moment that I place a charge capital Q with strength 10 nanocoulomb at point P. What is the force on that capital Q? The force on that charge capital Q is the charge strength, which is 10 times 10 to the power minus 9, times the electric field at that point, which is 4,167 I hat. And that's going to be 4.17 times 10 to the power minus 5 newtons in the direction of I hat. Thank you for watching.